this one. I think you guys know how to that. You guys have already signed up for this one. You know how to get into this one. See, you have signed up. You have already used this one in that, I think, NR 620 and 25. 620 and 25. 20, yeah, both classes we need SAS. See? Okay. So, SAS 2D, if you want, you can use this one, either this one, this one. See, even SAS Enterprise Miner, any of these, it doesn't matter. Okay. I'm mainly that I'm gonna work on this one. You know that unlike that regular SAS, you have to get the data, okay, uploaded into this server. It's working on a server, you know that, okay. You have to upload onto the server the data, okay. So it's gonna be look like this, okay. But anyhow, we can get back to this one later on, and then this is the syllabus, pretty much. This is the textbook, okay. This textbook, see, you can see. I think it has so much that detailed explanation for pretty much everything, okay. So these are that supplementary readings. We have all the reads and everything. Excuse me. And these are the chapters we are planning to cover, mainly the major topics here. See, principal component and factor analysis, repeated measures, second week. Third week, MANOVA, that means analysis, multivariate analysis. That's that multivariate format of analysis of variance, ANOVA and ANCOVA, like that. But we're not going to do MANCOVA, we're going to do only the MANOVA only, okay? I think you guys have already done ANOVA, I think, no? Analysis of variance, you have done already. Then you have to that do the comparison and contrast between that several groups, population, I think you might have done. So we're going to add that multivariate version on that one, okay? And then finally, we're going to get into the logistic regression. Those are mainly that we have 4 topics to be covered, okay? So and then when it comes to the discussion, that my same format, okay? That threaded discussion, even though you have a point whether you're going to do or not, okay? Like the earlier I used to do that one, okay? Because I want you to that mainly focus on these 4 and midterm exam and final exam. But this one has some kind of like a discussion based on that what we are doing in the class. But if you want, you can go ahead and then build up that discussion, okay? Whether you do or not, I'm going to give the full points for that one, okay? These mainly focus on this one. It's not hard, okay? We can go through all these, okay? And tomorrow that we have office hours, okay, from same time 5:30 to 6:30, and again Thursday we have a class, okay, like that, okay. During this time, let's try to cover that principal component analysis, okay. Let's see that what do you mean by the principal component analysis, okay. I'm going to build up some kind of a discussion, okay, systematically, okay. See. And then from this one, how could we gonna go back to the factor analysis? See? The principal component analysis, see, it's a statistical procedure that allows you to summarize the information contained in a large data tables by means of a smaller set of summary indices. That means that when you have like a large number of variables, so many variables, okay, let's say that you have like a regressive variables. You were trying to that fitting this one to that variables into a with the aid of these variables, you are trying to explain another dependent variable. I think you know what I'm talking about. There's so many that regressive variable or independent variables. With the aid of that one, you're trying to explain one dependent variable. In that such a situation that we feel like that some independent variables are redundant, unnecessary. So this is one of the that variable selection procedure. I think you have already done the variable selection procedures earlier, even in SAS 620, in for regression. No, if I'm right, because when you have many independent variables, how could you gonna get rid of that some variables and come up with the new variables? So that's what we are trying to do over here. Okay. So in this case, we are trying to do that instead of working with the like a high dimension, like a, let's say that you have a 10 variables, independent variables, you prefer to work with like a 2-3 variables. Okay. You prefer to see? Yeah, that's right. Yeah. Discussion question optional. Okay. Optional. Yeah, that's right. Okay. So how could we gonna get this done? See, that's why we say that, see, statistical procedure that allow you to summarize the information already contained in the larger data tables. Tables mean like a variable by means of a smaller set of summarized indices. That means variables. You're going to use the variables. You have a large number of variables, 5 variables, so sorry, 10 variables, and 10 variables. Instead of working with 10 variables, you can work with the 5 variables. With the aid of 5 variables, how could you going to explain that dependent variable? Later on, we're going to have something called the principal component regression. First, we have to build up the principal component in a such a way that all there are variances of the new variables. We're going to create the new variables called the principal component, which will be accounted for the like a larger variances. Okay, from the variances, that's what we have to do in this principal component analysis. We're going to extract some variables from that one, and then with the aid of that one, later on, we're going to move on to the factor analysis. In the factor analysis, what are you going to do? Mainly that your original variables will be explained with the aid of some hidden variables. Okay, you have to understand these two processes. These are interconnected. Okay, when we go through this one, you get a clear idea later on. You have many variables with the aid of the high dimensional variables, and we try to reduce the dimension. How could you gonna reduce the dimension? This is one of the methods in which that we're gonna write new variable with the aid of the older variables as a linear combination. Okay, as a linear combination of the older variables. Okay, we're gonna write the new variable, which are called the principal components, are written in terms of the older variables, all the independent variables with some weights. We need the weights. We cannot just simply write the linear combination. Linear combination has to be written in terms of some weights. Those weights are called the loadings. You can see down the road that when I go through that one, so with the aid of the loadings. Okay, so they have a name, loadings. How could we gonna get the loadings? Where these loadings are coming from? Okay, that's a one discussion. When you use that, what we're gonna do that as I said earlier, you have a 10 variables. The 10 variables, with the aid of 10 variables, we are trying to come up with the new 2 variables, which are being written in terms of the older variables. This way, you're not going to take out the variables. You still utilize the variables, whichever the variables are available in the beginning, original variables, you're going to utilize to come up with the new variable, which will be accounted for the higher variances for that the whole system at the end of the day. That's what we are doing in this principal component analysis. In contrast to this one, we're going to write the original variables sometimes in some cases, okay, with the aid of some hidden variables. That's called the factor analysis. Those are the things that we are trying to do over here in this principal component and factor analysis discussion. See, so later on that we're going to talk about this one mathematically, graphical representation. You can see down the road. When you see the graphical representation, you get a clear idea what's going on. We're going to rotate this one. Instead of having that several variables, we're going to have like a few variables. That few variables can easily explain the dependent variable. And when you explain that dependent variable with the few variables, which are called the principal component, this whole process called the principal component regression. So we are heading towards the principal component regression. Plus, factor analysis is something come along with that, and they both have the same kind of a procedures, results, and everything, but we have to uh, explain those in two different ways because they, okay. Uh, look at here, the PCA forms the basis for the multivariate data analysis. This is the beginning of the multivariate data analysis. This is a part of the multivariate data analysis. Multivariate means several variables will be taken into account at the same time. PCA being that Kaushi, that he first talk about this one, but it's formally formulated by Pearson. Okay. PCA is a very flexible tool and allows analysis of data set that may contain, see, for example, see, multicollinearity, missing values, categorical data, and even that imprecise measurement, anything, see. In this particular data set, you have the multicollinearity. Multicollinearity means like the correlation among the independent variables. Correlation among the independent variables are called the multicollinearity. Sometimes you have a missing value. Sometimes categorical data, continuous data, doesn't matter. In any form of data or imprecise measurement, still we can carry out this one, okay? So, let's look at this. Yeah. See, here the goal is to extract the important information from the data and express this info as a set of summary indices is called the principal component. See, you're going to extract some information. Information means variables, okay? And those variables will be written in terms of that loadings, as it we call the principal component, okay? Statistically, PSA finds sometimes the lines, planes, and the hyperplanes. See, it's going to be any dimension, doesn't matter. If you have a one dimension, we call the lines. If you have a two dimension, more than two, see, planes, two dimension lines, three dimension planes, more than three dimension, we call the hyperplanes. P dimensional, P standard for that, P stand for that number of variables that are available in the very beginning. So it will perform that p-dimensional space at the end of the day. If you have a three variables, see, if you have a two variables, you have a two-dimensional space. If you have a three variables, you have a three-dimensional space. See? So in this case, what we're gonna do, residuals, see, graphically the residuals measured. See, this is the new variable. In the beginning, let's say you have a two variable x1 and x2. Okay. I'm not talking about this y dependent variable. I'm going to say this is another variable, x1, x2, two independent variables. Those with the aid of these two variables, you are trying to get the new variable called the principal component 1. See how we're going to select this one in such a way that all the errors you measured with respect to this one should be minimized, while that you're going to do the distance measured from here to that point of that the point of projection should be maximized. Either this way maximize, this way minimize. See? See? This way it should be minimized. This way maximized. Okay. So we're gonna talk when we're gonna put everything into that system. You can see how this gonna happen, because with the aid of these two, I'm trying to write this one as a linear combination in such a way that the errors measured from these point to not here, not to the average, the way that we used to do in regression, not to they are the overall average, okay, or not to their categorical the group means in each and every groups, okay, not those. I'm talking about with respect to this line. If you measure this distance, errors should be minimized, but the distances measured from this 0 or the origin should be maximized in such a way that we're going to build up that when you do the calculation, everything will be come up in such a way. This is a graphical representation of the principal component at the primary stage. Okay, later on you can see. Okay, the variance of score is maximized. This is the variance. Variance means the error. Okay, those are the error. Okay, so these are coming under the broad title of the factor analysis. Principal component. Principal component analysis has been utilized as like a extractional procedure. In extractional means like in which that we're gonna extract some variables, and then with the aid of extract some principal components. With the aid of those principal components, we're gonna explain the regression. Okay, we are doing this one in order to build up the regression. Okay, that's a kind of like a basic idea. So look at here. This is what we're gonna do. See, the picture below shows what a PCA is doing to compound. I'm going to PCA in principal component analysis being abbreviated as a PCA, doing to combine 4 measured Y variables. See, original Y variable. They say X1, X2, X3, X4. Instead of that one, I use the Y1, Y2, Y3, Y4. These are independent variables. With this one, you're going to, with the aid of these 4, you're going to write a one variable, new variable. You create a new variable. See? The model can be set up as a simple model. See, I'm going to call that one either C or PC, principal component. How could we going to select how many principal component do we can build up? That's discussion we're going to build up systematically. Okay, look at here with the aid of this one with some weights. See, these are weights. I wrote, instead of working with like a, let's say this one, test 1, test 2, test 3, test 4. Okay, being explained to that GPA or something like that. Okay, or the admission, chance of admit is admit to that any graduate program or medical school, law school, or anywhere. Instead of going for these 4 tests, I'm gonna combine the 4 tests into one and then work with this one, and then we can build up the regression from that one. So now instead of working with these 4 independent variables, there's only one independent variable, which is for the principal component 1. How could we gonna get the weights? See, these are observable. See, these are observable variables. These are, you have already observed these 4. But that's the procedure that we're gonna discuss throughout this whole time. Okay. So the weights, with the aid of these weights, we have written this one. With the aid of this one, we have written. See, that's what we call the principal component analysis. Because instead of working with these 4 variables, I can extract and then extract only one principal component. See? Can I build another principal component? Yes. Can I keep going? Yes. How far we can do this one? Who gonna change that the principal component from one from the another one? The weights. See, the weights will change. See? We can have a different weights. What do you mean by the weights? Those are called the loadings. These are called the loadings. See? These are the loadings. So do you have a new variable now? Instead of working with this variable, it's easy to work with this variable. Since it's in this dimension, look at that. We have 4 dimensions here. Now I have 1 dimension. It's a kind of like a dimensional reduction procedure. See, now I have 1 dimension. I need 1 variable to explain the independent variable later on. Then on the other hand, its counterpart, factor analysis. If you look at the factor analysis, sometimes these very test, the way that how we have performed, being completely determined by some hidden variables. Those are unmeasurable. We cannot measure. See, look at the same thing. See, it's that opposite of that one. It is a kind of the model of the measurement of latent or lurking or hidden variable. With the aid of the hidden variable, how many hidden variable can we take into account here? As many as you want, but there's a cutoff point for that one. Based on different procedures, criteria, we can figure out that how many factors to be included in order to explain our original data, see, original variable, see. Now here we do the other way around, see. The latent variable cannot be directly measured with a single variable, see. These are such as the intelligence, because when you're going to talk about the test score that when you see the test score can be completely determined by the intelligence. Okay, well, in a sense, another one, social anxiety. These are that soil health. Those are those kind of a variables we cannot measure. Those factors we cannot measure. Instead, it is seen through the relationship. See, it causes in two set of y variables. See? See? Instead of that one, see here B1, B2, B3, B4. Sorry, you have to have this one weights to B1, B2, B3, B4. Like that. This should be B3. This should be B4. See? Like those are weights. See? I'm gonna write the original variable with the aid of this one, this factor. See? How? See, when you write that one, it's like a regression. It's come along with the error term. Unlike in the principal component, in factor analysis, we have an error term. See? This is like a rough idea. See, okay, I wrote that y1 with the aid of b1, see, and y2 with the same factor. See, can we include some several factors that going to affect to the test 1, test 2, test 3, and test 4? If these are different kind of a test, let's say math test, language test. Some people are some computer science and those kind of a test, but different people are have their skills in languages. Sometimes they have like a technical skills. Based on that one, see here we're going to focus on one hidden variable. Let's say only skills in one subject has been utilized in order to write the test score of all these variables. Okay, that's why we need the principal component for us to extract this one. With the aid of this one, I'm going to extract this one. Okay, try to understand what we are doing over here. See, I'm going to go in a summary fashion. Okay, so I'm going to build up this one, principal component analysis. See, in this one, I built up this, and now with this y1, I'm going to explain with the aid of hidden variables. So this is connected. Okay, you had these variables, measurable variables. See, these are measurable variables, but those variables are always too many in a one on one side. That is, it's too many of them. Okay, so see, too many of them. I reduced the dimension and I wrote that one with the aid of this principal component 1. There's only one variable. Now these variables can be written with the aid of factor analysis. So they are connected. Okay. Okay. Y1, Y2, Y3, Y4. I can written with the aid of factor analysis. See? Like this. Okay. Y1, Y3, Y4. See? So the factor analysis will be utilized in order to write the original variables. See? With the aid of the hidden variables. And principal component analysis we're going to utilize in order to reduce the dimension of that particular setting. Okay? Okay. And eventually I'm going to get this guy and explain another variable called the dependent variable. Then it's called the principal component regression. Okay, that's how they are linked. Okay, so the original data will be written in terms of the latent variable. That process is called the factor analysis. See? I'm utilizing only one factor. Let's say intelligence being utilized, or math skills being utilized in order to talk about all the 4 variables: test 1 score, test 2 score, test 3, test 4. If you're going to say for an example, these are test scores. See? The data of this one. Contrary to that one, in principal component analysis, we extract how many that new variables to be included in our discussion. We decided, okay, this here 1 is enough, but how could we gonna decide how many to be included? That discussion we're gonna build up. Okay. So we mainly use in that principal component analysis as a like a extractional method. Okay, variable extractional method. See, a little bit remember this one. With these two words, get familiarized with this one, orthogonal and then orthonormal. See, orthogonal means factors or components are uncorrelated. What's going to happen once you build up the principal components? Those principal components are uncorrelated. They were not correlated in the beginning. See, the beginning, if you build another principal component with the aid of the weights and everything, if you get the two principal components, new variable, those are uncorrelated. There's no covariance matrix for that one. There's no covariance between, there's no correlation. But you have a correlation among what? See, sometimes among these ones. Among these ones, correlation. See, that's the correlation we're going to take into account in order to build up this discussion. In the beginning, Y1, Y2, Y3, Y4, they have a correlation among themselves. But that correlation will be taken out when you build up the principal components. That's another disadvantage of the principal components. When you get several principal components, you don't have a correlation among those principal components, except for they are having the correlation among themselves. See? You have a correlation among these ones. And the PC to this one, that correlation, we have that one too. See, that's why, see, then the orthonormal means factors or components are scaled in a such that the sum of squares of the coefficient for each variable is 1. Okay. When you get the orthogonal means factors or components are uncorrelated. Orthonormal means factors or compute that these components are scaled. We can scale them. We're going to do that one down the road. We're going to scale in such a way that they are sum of squares of coefficients. Each variable becomes 1. Loadings are the correlation coefficient between the observed variable and a factor. What that means? I'm talking about this and that. This and that. This and that are called the loading. See? The W1 is the physical interpretation of this one is nothing but the correlation between the new variable and the older variable. Older variable we're going to call the observed variable. This is observable. That this loading is nothing but the correlation coefficient between these two. And so do we see other ones too. See, W2 means the correlation coefficient between PC and Y2. Correlation coefficient between the PC and Y3. The correlation coefficient between Y4 and PC is called the W4. Those are the loadings. Remember that one. This is provided that the factor solution is an orthogonal, that is, factors are uncorrelated. Factors means these are the factors. There's not this factor, and if you have another principal component, those are factors. So for the components, doesn't matter. In the principal component analysis, we used to call them component. In factor analysis, we used to call them factors. If this one and if you have another one has been written in same like in a linear combination of the order variables, those two are uncorrelated now, the way that we built up this one. Okay. So remember a few things in your head. In the beginning, among these variables, original variables, they are correlated. See? Highly or lessly correlated among themselves. There's a covariance matrix for this one. But once the way that we built up the principal component, the way that we're going to write this one as a linear combination of the order variables, the principal components would not have any correlation among themselves. But still, principal component and the order variable will have a correlation as well. That coefficient is nothing but the loading. So we are looking for the loadings. When you run this principal component on SAS, one shot they will be listed, but you don't know what they mean. They are called the eigenvalues and the eigenvectors. They have a name, okay, mathematical name. You have to get familiarized with that one in order to explain to that your audience at the end of the day. You cannot just look at the printout and say that, hey, this is the principal component. Look at that. If you go back to this one, look at this in example. I have already uploaded this data set too. Okay, it's under that data folder. You can see So see, you have to run only this one only, see, one line. In that particular data, I have a 13 variables. I don't like to work with the 13 dimension. I want to reduce that one to that few dimension and come up with the new variables. So it will, let's run this one a little bit real quick, okay? I have this now, yeah. I have uploaded this one into the server. From the server, I pull out, okay? So I call this one GSP. Gross state product, okay, gross state product. Okay, real quick, I'm going to show this one, okay. See how they get the income for their state: agriculture, mining, construction, manufacturing. That's kind of a like this. See, manufacture, transportation, communication, energy, like that kind of a data set. Okay, we can go to data later, but I'm trying to show you this one. See the correlation. You can find the correlation among those variables. See, it's a the correlation. See, there's a correlation. See, some are highly correlated, some are positively correlated, some are negatively correlated. See? And in addition to their correlation, they have a covariances too, because they're going to be like correlated among themselves plus that correlate with the other variables as well. See? Then when you run this one, you can see their correlation. If you go ahead and run principal component analysis, printcom, you don't have to say how many variables. If you want a certain number of variables, you can restrict here, but for time being, but I'm trying to show you here that what you're going to see. See, you see this one, eigenvectors and eigenvalues. See, you see, these eigenvalues. What do you mean by the eigenvalues? See, these are, see, now they built up principal component 1, 2, 3, 4, 5, 6, 7, 8, 9, 13 of them, because we had or 13 variables to fitting into that number of variables. We're going to have a new variable called the principal PC1. PC1 has been written in terms of what? AG, mining, construction. See, these are the older variables. In my case, this is like a Y1, Y2, Y3, Y4, all the way to Y30. This is PC1. These are the weights, as I said, W1. See, W1, W2, W3, W4. You know, this was a physical interpretation between this one. That's the correlation coefficient between principal component and the agriculture. See? In another way, that's a physical interpretation. How do you get the loadings? How come we get the loadings from where? The loadings are coming from where? Loadings are coming from the eigenvalues. But the eigenvalues, how many eigenvalues we can build up over here for these 13 variables? In the original data set, we have 13 variables. See, these are the variables. See, they are mean and standard deviation being listed too. And but you see, look at their eigenvalues, something called eigenvalues. See? These eigenvalues, there are differences being given. Eigenvalue between the two consecutive eigenvalues being given over here. Their proportion being given here. The accumulation is given here. Eigenvalue is nothing but the variance carried by that particular variable. That's a variance. It's the variance, okay? We can see that one. I'm going to show you. But I'm trying to say that these are the loadings. See? Look at this one line. It's not hard. But you have to know how to explain to your audience your printout. See, results. Then we have something called the scree plot. From the scree plot, with the aid of the scree plot, you can you can determine how many principal components to be utilized in order to do the regression later on. These are independent variable. Let's say these are independent variable. You really need to explain another variable with the aid of this one. But I don't need these too many variables to explain that my dependent variable. It's like you have already learned that variable selection procedures. Can you remember forward selection, backward selection, stepwise 3 method? In addition to that one, this is a very powerful tool in which, without taking out variables, while keeping the variables with the aid of their own variables, you can come up with the new variables to explain the dependent variable. This is a very powerful tool than that forward or backward or the stepwise selection methods found in regression. You see, you never gonna take out the that agriculture or mining or construction or any of these variable like in that selection methods. Can you remember? Some variables are taken out, added, taken out, added, taken out until it becomes so stable. But here not the case. Your original variables not be taken out. You are trying to write that one with the aid of these ones as a linear combination. Okay. Okay. Let me see. Can you access the data? I think the data you can access. No, can you access, David?
No, I have access right now in, if I go to SAS Studio, I still have ANA 610 and ANA 620 are the courses that I can actually get to.
Can you remember on the syllabus, it says that you can, on the homework, homework, can you access something called the remote desktop? Because this is the way that how they have set up. But I got the data. I went to this one. I went to that. They have. I think.
I don't know about anyone else, but I don't see when I go into.
What do you mean by the remote desktop? Do you have something called the remote desktop?
I do not.
Okay, don't worry. Okay, I'm gonna fix this one. Give me 1 second. Okay, don't worry. Okay, let's go ahead and get the data in another way. Okay. I'm gonna go to this website, KISS. Okay, I'm looking for that one. If I have that one, okay. Otherwise, I can. Yeah, that's okay. So I got it from here. See, I went to their website. Okay. So you just on that on any search machine that you can type in that KISS data. See, California Health Interview Survey data. See, and then this public use data files download now. Because I have already signed in for this one. Login. If you, because I thought that you guys know how to get into login. Okay. So
yeah, with the previous courses, we were sent a course code, and that course code gave us that access to all the folders. So we had those.
They didn't provided anything like that. Course code you need to get
Right,
the remote
right.
remote desktop or this one. I'm talking about this one.
Oh, for that, yeah, I went to that website already. I just didn't sign in. I didn't create an account.
Okay, yeah, I think okay. There's creators on that one, and I already created this one. I think.
But for your SAS folders, that all the other courses have had a course code. And
oh
then,
no. Yeah, I don't know that about that one because they didn't even give the course. See, they didn't give any course code or anything. Just that's why I thought that you guys gonna have like any difficulty. Then I thought that okay, I better off to take the data in a different way. Even I cannot access that one too. This place. This
okay.
what we call the remote desktop. I cannot access. That's why I went to this their original website and pull out all the extract the data. That's what I did. So if you go to this one, see. Yeah, I got the data. No. Publication program. Philippine interview survey data. Yeah. That I had a data that, but I was trying to that upload into the system. It won't allow me to upload. Analyze data. Where's the download? Let me see that. I got the other day. No. Should be somewhere data. Okay, browse publication of the publication. Because I have this one in this folder already. See, download. I download. See, It's a zip file, see? From this one that I uploaded into the system, see? Let's see that where this.
Is there any way you can put that in the announcements? You can just attach that maybe? I mean, I can try to fiddle with it and download it, but
You cannot download this one from this website, no? Go to this website. I think, okay, that's the best thing to do. Okay, let's go to this website. I'm gonna type in again, KISS data, CHIS data. You can just go to any search engine and then it is over there because that's how I got the data. You're talking about the homework data or the data that I'm using right now? Which data, David, you are talking about?
Oh, I'm talking about well, either one, but the homework.
Oh,
data-
either one. Okay, that's fine. Okay, that if you need that the data that I'm working on right now, PSA GSP data, it's in the data folder.
Okay.
Already have a folder. Can you open it? No.
Yep. I've pulled that down to my local computer. I haven't uploaded it.
Yeah,
to
but the
SAS.
KISS data in the homework. Let's go to the homework one. See this data. See this data. See this one. I thought that we have to go to the remote one. I couldn't even access that remote one. What I did, I went to this website. The KISS data set, and then UCLA Center for Health, see? Health Policy Research. And then when you want to download data, it's a public use data. Download now. Okay, here, yeah, that's right. Because I am already in, see, I already signed up for that one. You can give the name and then email address and then you sign up. And 2009 KISS data, see? So you have all the information here. See, it's been given in SAS, SPSS data, see? 2009. But you don't pick the adolescent one to child one. You have to get the adult one. See this one. Download this data for the homework. Okay. I have already.
So there's no way you can drop that into the course.
Yeah, that's what I was trying. Exactly. That's what I was trying to do earlier today for the data folder. But it seems like, I don't know, it's blocking me for getting that. Maybe that is so huge. See, I can pull this out. See, this is already in SAS. This is XPT data. That's the one that I have changed. See, I uploaded that into the server first. See, and then converted into SAS data. See, this one. Let's try to. I'm gonna try to pull that out and then drop into that one. Let me see. Let me see. I'm gonna go to the data. PCA effect analysis. Okay, the existing. Okay, I'm gonna. I was trying to drag and drop. Okay, let me see. It won't. I think it's so. See, too big. Okay, let me see. Okay, it's already there. I think it's there. Can you see? Go to that data folder under PCA/factor analysis and then adult. I drag this one and drop over there. If you want, I can drop even adult XPT too. You see? For homework.
I see in that data folder. I may have to reload to get everything. I see under the PC/FA.
FA, yeah, exactly.
There are
And then
two different ones, PCA_GSP, two with that name.
two with that name. Okay, well, let me see.
Let me see, I just reloaded. Now I have adult there also.
Okay, I'm gonna put this one to XPT one too. Okay. Okay, let me see. Yeah, I have another adult one in XPT, the other one says, and you have a PCA, GSP, PSC, GSP, it has been, I think, uploaded, not twice, one in
Okay, yeah, we have now.
one CSV file, the other one is SAS file. The PSC,
Okay.
the one that one I'm working on now, that TCA, GSP, that the gross state product, principal component analysis, those are in two versions, one for CSV format, the other one in SAS format. The
Okay.
adult one, I have a SAS one and XPT.
Okay.
Both. No? Can you see? Four of them?
No, I see there are four now. There's
Four now,
adult
yeah.
all lowercase, adult all uppercase,
Exactly. Yeah.
and the two PCA_GSP.
Yeah, for the homework, then you don't have to worry about go to the remote this desktop.
Okay.
That's the data that you have the data. I was trying to drop that one earlier, it didn't work. See, but if you really want to get it that one and then install somewhere, I mean like download somewhere, you can go to this website and sign up for the website and you can access, and then especially that along with that one, you really need that dictionary for that. They've been coded, all the variables been coded because they were too long. The names of the variable, they were being coded. It's coming under, okay, if I pull out something called the dictionary. Okay, even over here we have that one. You see, data dictionary. See, if you want, you can then open up and then have a look at it. See, they've been variables being coded. See. So sometimes you might need it, that one. See here that when we go to that homework later on, we can talk about later on. But anyhow, that since we have already brought this up, see, we're gonna keep see AF62 to AF72, AJ29 to AJ34. See DSTRS, distress 12 to distress 30, BMI, see body mass index, the bench 12, see education, blah blah blah. Those have been coded. So let's say for instance, AF62, if you go ahead and look at under, should be in this dictionary, should be further down. Oh no, those are the dates. So they have called a variable codes under that topic. Let's go up and then scroll down slowly. Okay. This one. See this one. 5, which is on page, I think 20, on 17. Sorry, 17. See, page 17. See, when I say here AF62 to AF72, AF62. AF62 here. See, any month past 12 months, felt worse, feel nervous, worst month. See, feel hopeless, feel restless. See, blah, blah, all the way up to 72. Like that. So they've been listed too. So what I'm gonna do, I can drop that one too. That I'm gonna create a new unit policy. Only if you need to under the same thing, I can just drop that dictionary as well. And so drop here under data. Let me see, add the existing. I'm gonna get that one too. I have that dictionary too. I to 50, 30, like, so, number, which one? Yeah, that, yeah, you can see that one too. I uploaded that one too. I dropped that one too, data dictionary. You go to the data folder again. In the data folder, you can see that even the data dictionary, the same thing that I see on this one. And on that one, you go to number 5 to get that the code. See, data dictionary variable listing. Okay, when you open that one, you can get there that how they've been coded as well. Okay, because of their lengthy names, because of that they were being coded in this survey. So I think you have everything that you need. And the data set now I'm working on that for that principal component of that example. It's called the PCA GSP. CSV one is the one that I'm using. And if you want the SAS one, you can directly pull that out and then working on that one to make sure that you're gonna upload that one to the server first. So this is the one we gonna talk about that one tomorrow. This one when we go through that homework, but you have that one. Okay. So I have even that, see, AF62, see, I have already listed everything that what we're talking about over here. It's not necessary to be the same variable that I'm talking over here. You can keep as many variables, that different kind of variable for your discussion. With that homework questions being set up, see, you see, identify 10 to 20 variables in the adult 2009. See? They get this data and then change that name to the adult 2009 like that. But anyhow, that since we are on this one, this data set are already that, see, this is the one that I uploaded into this server, PCA, see, PCA GSP CSV, see, that's the one I'm working on that one. So you have that one too, see, file names, and then I'm gonna change the name to GSP. I'm gonna open like a new, see, in this library, we have a work library, see, you have a GSP, it's a temporary library, and then temporarily we're gonna keep over there work, even you don't have, see, you don't have to put the work because since it's in a temporary, you just simply put the GSP enough, okay? But what I'm trying to say over here, what we were discussing over here, that when we get these loadings, these are the how the loadings being built up is the discussion that we have to build up over here, okay? So like over here, so this is the one that I'm interested in, how these are called the loadings, how we get the loadings, okay? That's the part. At the same time, we just get familiarized with these terms, orthogonal, orthonormal. What do you mean by the loadings? Okay, so what I'm gonna do, I'm gonna show you what's gonna happen, okay? Here, because in order to save the time, whatever that we have a notes, I'm gonna show you over here that because in that way, I don't have to write everything, because if I'm gonna write, it takes a lot of time, okay? This already been done, see? Let's say that you have a 2 variables, okay? I'm gonna say this is like an English test. It's like a math test, 2 variables. Even though this is not a dependent variable, they both are independent variables, okay? Both are independent variables. They both are independent variables. I'm talking about 3 observations only. just 3 observations. Okay, just 3 observations. Okay, see 1 0 minus 1. I mean, like for the, you don't have to that practically you might be thinking, well, how could we get a -1? But doesn't matter, that just let's say some numbers. Okay, this kind of a thing we call the column vector. Column vector means like you have a row, see, 3 by 1, 3 by 1. See, this is the number of rows being given first, and the number of columns given second. See, 1, 2, 3 rows, 1 column. So the data being given by this vector, see, column vector. See, so for the second variable, for the other variable, 3 observations. See, y1, y2, y3. So they are numbers. See, observation 1, observation 2, observation 3 put together we call data. See, these are data. Now what I'm going to do, I'm going to combine this one together, both. Okay, combine. But I'm trying to show you how we're going to get that loadings. The loadings that you saw in principal component analysis, in which that we're going to change the dimension and come up with a new variable. You really need to know that what these loadings are. You know this y1, y2, y3, y4. In this case, you know x1 and x and y. For my convenience, for mathematical tractability, easiness, I'm going to work on 2 variables. Okay, but in your case, that in that particular example that I had been going through earlier, I had 13 variables, but I don't like to work with the 13 variables. I love to work with only 5 variables. Okay, so I'm going to combine this data. See, look at, I combine this data. See, in one matrix. So now we have 2 rows, see, 3 rows. I'm sorry, 3 rows and 2 columns. Okay. So when I
Okay.
put that one, go ahead.
Sorry to interrupt again.
That's okay.
It looks like the one folder, one file downloaded correctly. It's PCA GSP.SAS7B DAT. But the adult, I've tried loading that down, both the XPT and the SAS files, and they're both coming up size 0.
Oh, they were
And
not there? Oh.
Yeah, I've gone in and unblocked them, but they're all coming up size 0.
Okay, then the best thing I think that in your side, okay, I was trying to that send to you guys 2 data, but best thing, go to that website and pull out from there. I think that's the best thing to do. I think that okay, go to the website, KISS, as I did earlier. Okay, KISS data. See, go to see the same thing like that. See, that's the best thing to do. See, go here, UCLA Center for Health Policy Research. Sign up for that one. So from this website, you can pull out the data from this one. See, download. You cannot download until you're gonna sign up for that one. Okay, I can do it because I already sign up for that one. See? This data. Then I went to here. I download. See, KISS 2009 adult. See, it's a zip file. See, it's a zip file. See, you have to unzip that one. If you can do on your side, I think you can easily get that one. Unzip and then one side. Oh, sorry. Then it had gone to over here. See?
Okay, I think I've got it. I've got it downloading.
I think, yeah. Then you have to unzip that one, and once you unzip, see, you go inside. See, that's the same thing I showed you. If you go inside, you can see all these. See? Then from here, you go to that server, that the SAS, and then upload it. Upload this guy. Because you have to upload.
Yeah, I got the other one uploaded into SAS, but I just didn't get the adult because it came down to size 0.
Oh, but this time okay, no?
It's downloading right now to my
Okay.
computer, and then I'll unzip it and put it up in SAS.
Yeah, put up in SAS. Okay, hold on. Okay, there's a SAS one that we had. I already see and the XPT that I transport, I put into the transport folder, and from the transport folder, I transfer into the data out. You don't have to do like that. You can keep in any folder that you want. See the way that I have done. See. They were already in. See. But they were in my this folder. Now data out folder in that library. See, I used to have on this one from the out file. You see, I transport that one from that file to this one, this folder. So see, go this one. See, data out. And it's a SAS file now. And later on, I changed that one to test. See, change the name of that one. Adult 2009. I changed to test for my convenience. You don't have to, but okay. So this is where that I have uploaded. Once you upload over here, so to the server, see, you can upload to the server from here. See, you know how to upload, see, from here.
Yep, I have it uploading now. So
Yeah, okay. Go to
I'll
the
just-
wherever you have that one, choose the file, and from where you have, see, you can bring it to that one. Okay. So let's say that downloads on the downloads. See, under this one, see. That's it's not a zip file. You have to unzip that one for sure and then upload over here. Okay. And upload, once you upload, it's in that XPT file, but it has to be converted into SAS file. See?
I just downloaded the SAS file and I'm uploading the SAS file.
Oh, okay. Then it's easy.
I don't have to do any conversion.
Yeah, you don't have to go to the XPT then. Yeah, but what I did was I get the XPT and converted that into the SAS. You can straight get to that one. Okay. And then keep in one folder, because I was doing over here that from the transport one, I just put into the data out folder. You don't have to. Then I transfer from data transport folder to data out folder and give it a different name, adult 2009. Earlier it came at like adult XPT, now it's called the adult 2009. So, okay. So let's get back to where we were we were talking about earlier. See, so now I put that since two variables, I'm working on two variables. Okay, I'm working on two variables. Now what I did was I got their mean value. See, 1 plus 0 plus -1. See, and divide by 3 and mean vector. See, they both will produce 0 and 0. Then I need to build up the covariance matrix. Covariance matrix is the key part in the whole discussion. That means the correlation and covariances among these given variables. See, covariance matrix is nothing but S minus, think this guy, S minus S bar, transpose time S minus S bar. So once you do that one, it will have 2 by 2 matrix. Variance of X here, variance of Y here, covariance of XY here, covariance of XY being repeated. That's what you're going to see at the end of it. On the other hand, if you have a covariance, how do you convert that into correlation? You get the covariance divided by the square root of the variance of X and variance of Y. This is the formula. See? This is how they're going to convert into correlation. Either you use the correlation matrix or covariance matrix. See? Either way. But I'm using covariance matrix. How do you build up the covariance matrix? With the aid of your data matrix. See? Once you have this one, just plug in that what we have over here. See? S bar 0, 0, see? This is the my transpose. Transpose means you're going to change reverse columns and rows, see, of that S. You earlier had like a 3 by 2. Now you have a 2 by 3. And then multiply. You're going to multiply. How do you multiply? See, 3 get cancelled off. You're going to end up with 2 by 2. See, this element to this element, this element to this element, this element to this element. That's how we do that. But you don't do anything by hand. I'm showing over here what's going to happen in that behind that when you run the PCA, how they generate the eigenvalues. Okay, this whole purpose that how to get a how they built up the covariance matrix. See, the first row, first column. This is the first row, first column, whole thing. You go one by one, this to that, this to that, and this to that. You build up this location. First row, second column, you build up like this, element to element. And see, second row, first column, this part. And second row to second column, you build up that like that. Then you're going to build up this covariance matrix. This is the covariance. Look at 2 and 2 are the variances of X and Y. This is the variance of X, this is the variance of Y. These are the covariances of, that means they were negatively correlated. See, negatively correlated. Now what's going to happen? We decompose this one. We split this one into 2 parts. This covariance matrix will be decomposed into 2 parts. One part called the scale part is called the eigenvalue. Direction part called the eigenvectors. That's how you're going to see on that you print out eigenvalues. Eigenvalue is nothing but the scale part of your covariance matrix of the original data. See, these values are nothing but, see, these are nothing but, see, the covariance, see, this one, this is a correlation. If you want to convert this into covariance with the aid of this given relationship, see, this relationship, see. If you have a correlation, you know how to convert it to covariance because you have to multiply correlation by these two. Then you can get the covariance, or you can get the covariance like this way. We're mainly working on the covariance. Covariance will be split into 2 parts. The scale part of the covariances are called, when you split, eigenvalue. Their counterpart is called the direction part called the eigenvector. How do you find the eigenvalues and eigenvectors? Covariance matrix should be multiplied by the eigenvector equals to eigenvalue times eigenvector. That's how you're going to get this eigenvalue. That means this is my covariance matrix. I call that one C. Eigenvector I'm going to call U. Eigenvalues I call lambdas. Eigenvector, see, covariance times U. U means the eigenvector. Then I'm going to pull out this one in matrix C minus lambda. I means identity matrix, which is 1, 0. See, for this equation to be solved, the following has to be following has to happen. That means this part determinant, what is called the determinant, means the size of that one. See, or the magnitude of this one has to be 0. So you know C is nothing but the covariance matrix minus lambda times this one. Then we're gonna see, we're gonna little bit simplify this one. 2 minus 2 minus lambda. 2 first element. From this one you get the first element. See? Minus 1 minus lambda times 0. Minus 1 minus lambda times 0. See? All the elements. See? We're gonna little bit simplify this one. Later on, we're gonna how to determinant mean nothing but you get the cross product. You get these two multiply, and make a equation. 2 minus lambda minus 1 minus 1 minus 2 minus lambda times 2 minus lambda minus 1 minus 1. See? Then once you solve, you're going to come up with the quadratic equation in lambda. See, that's called the characteristics eigenvalue equation. It's nothing but, if you go ahead and check, lambda squared, the trace of C. This is nothing but, how do you get the 4? 4 is the trace. Trace means that that's the sum of the diagonal values. You don't have to go in this route. You can easily build up this characteristic equation, lambda squared minus trace of C. If you know the covariance matrix, you definitely add these two, which is this one, plus, see, plus the determination. See, this is the determinant of this matrix. How do you find the determinant of this matrix? See, 2 times 2. See, how do you find the trace? 2 plus 2, 4. Determinant, how do you find? 2 times 2 minus time minus 1 minus 3. That's how you got that one. That's either going through that route and get this equation, or just by looking at the covariance matrix, you can get that one. You don't need to go through this route. You know the covariance matrix, your characteristics equation is nothing but lambda squared minus the sum of these two plus the determinant of this one, which is 3. It's the same thing we did. Either way. Now you saw that one. Then you get the lambda equals 0 and 1. Okay? 0 and 1. Those are the eigenvalues. That's how you get the eigenvalues. Okay? If you have a 13 variables, you have a 13 eigenvalues. If you have a 2 variables originally, you have a 2 eigenvalues. See? If you add these two, see, sum of the eigenvalues is nothing but what? Is equal to the trace of C plus, that's the sum of the variances of X and Y. See, these are nothing but the eigenvalues. The sum of the eigenvalues are nothing but the sum of the variances of original variable. They see 3 and 1. But they are not, you cannot say this is the eigen, this is the variance of the first variable, this is the variance of second variable. No. Variance of the first variable is 2. Variance of the second variable is 2. It's a different thing. But if you get the sum of them, that sum is equivalent to the what? Eigenvalue. Sum of the eigenvalues is same as the sum of the trace, or the equal to the trace of the covariance matrix, and the sum of the variances of X and Y. The product of the eigenvalue is nothing but the 3 is equal to the what? Determinant of C. See? The characteristics equation you can build up like that. What are you gonna do? You're gonna put this back into this equation again. See? Back into this equation. Okay, lambda equals 1. I'm gonna put it back into your equation you originally had over here. See? I'm gonna go back here. See? See here for this one, this equation. I'm gonna get back to that one. See? And this one, see? This is 2 by 2. This is also, you, since you have a 2 variable, you have to have a 2 components for the eigenvectors. These are eigenvectors. One in the direction of one direction, this is the other direction. Then you plug in that one over here. You simplify U1 and U2. See, little bit you simplify. Then eventually, see, you get 2 equations. See, this one times this one is this one equal to 0. This one times this one equal to 0. You get 2 equations. They both will reproduce the same thing. That means U1 equals to U2. So your one of the eigenvector is U1 and U2, and U1 and U1. That means 1 and 1 you can substitute for that one. Then you're gonna normalize. You normalize means you're gonna divide that each and every one by the square root of the square of that one. See? Those are called the loadings. I'm heading towards the loadings. See? So you got the eigenvectors now with the aid of, for given eigenvalue lambda 1. See? Lambda equals 1. You get the this the whole thing is called the eigenvector. Eigenvector has a 2 components because you have a 2 variables in the beginning. See? Then we got this one, U1 equals to U2. That means both equation will give you U1 equals U2 and U1 equals U1. U2 will be replaced by U1. For U1, you can substitute any number. They both will carry the same thing. So what I'm going to do, I'm going to divide this by to normalize this one. See, you have to normalize 1 over root 2 at 1 over root. I'm going to do the same thing for other eigenvalue. See, I'm going to do the same thing for the other eigenvalues. Okay. So with that one, what's going to happen? See? So look at that. I plug in that lambda equals 3 here. I'm going to call that one V1 and V2, the second eigenvector, and solve that one. When I solve that one this time, you get this equation and this flow to this flow, see, equal to 0. If V2 equals V1 minus V1, the other one, V2 equals negative V1. That means V2 equals the negative V1 in both cases. That means when V1 equals V1, V2 is negative V1, 1 is 1. If you put the plug in 1 for V1, you can get any arbitrary value for that one, this negative 1. Again, I do that same thing that I did earlier. Then the loadings are nothing but your eigenvectors times the eigenvalue. Look at the eigenvector. Eigenvector, you have 1 over root 2, 1 over root 2 earlier, when lambda equals 1. That should be multiplied by 1. Then you get the loadings. 1 over root 2, 1 over root 2. The second loading would be what? See? Second loading would be, see, V1 and V2. See? See? And multiply by their loading, their eigenvalue. So then you're going to have this loading. So these are the loadings. See? I'm going to write the loadings in this direction for X and Y. See, this is for X, this is for Y. See, 1 over root 2, 1 over root 2, root 3 over root 2, negative root 3 over negative root 2, this way. See, this is the principal component 1. See how much being contributed by this guy is nothing but the loading. See? For lambda 1, my principal component is what? 1 over root 2 times X. See, 1 over root 2 times X plus 1 over root 2 times Y. My second principal component in this case, root 3 over root 2x, see, this one times x, this one times y. See, those are the loadings. See, look at the loadings. We saw that one in the beginning, I call that one W1 and W. Those are nothing but loading. How do you get the loading? Loadings are nothing but the eigenvectors being multiplied by the eigenvalue, square root of eigenvalue. That's how you get that. The same discussion you can extend for any number of variables. See, that's how you're going to come up with the new variables. See, with the aid of all the variables, see, X and Y, I came up with a new variable called the principal component. I didn't discard or throw away my older variables. And I have another one too. You can build up same number of principal component as that original number of variables. I had 2 variables, so I'm going to build up 2 components. But I don't know whether I really need both of them. That's the discussion we built up later on based on certain criteria. Okay, so look at that. The communalities means what? Each original variable's total variance. We are looking for the original variable's total variance that can be explained by the PCs. See, you go to the original variable. How much? This way. I'm going to go this way now. Those are called the communalities. See? I'm going to go this way. I go this way. I built up the principal component. See? Who are these? These are the loadings. How do you get the loadings? With the aid of the eigenvectors and eigenvalues. How do you get the eigenvectors and eigenvalues? With the aid of the characteristics equation. You saw the procedure earlier. We built up piece by piece and we came to over here, assuming that we have 2 original variables. See, original independent variables. So I go this way and see that for X, how much variance of X being explained by this guy? How much variance of X being explained by TC2 is that one? See, if you're gonna square that one, see, if you're gonna square those in that direction, see, 1 over root 2 square plus root 3, that will becomes 2. See? Look at the 2. See, you can remember the variance of X would be how much? The variance of X is nothing but 2. That has been split among these 2 principal components in this way, this much and this much. How much? 1 over root 2 and 2 root 3 over root 2, that much being, the variance being split. How much variance you had? 2. If you square this one and square this one and add together, you're going to come up with what? The variance of X. And so does with this one, 1 over root 2. See? The second one, see, communalities, see, for y, 1 over root 2 square plus root 3 over minus root 3 of the square, come up with the 2. So that's why we're going to say sum of the squared loading is equal to the eigenvalue. See? Sum of the squared loading is equal to the eigenvalue. See? That's a this one is that communalities. Communalities, how do you gonna get that one? By communities means nothing but how much each variable's total variance has been explained by the principal component. Original. See? This one, see? That's what, if you want to give a physical interpretation for communalities, if you see the communalities means nothing but how much each variable's variance, total variance, see? That can be explained by the pieces. That one, see, that's the total variance of x experienced by PCC, explained by PC1 and PC2 both. Total variance of x has been explained by PC1 and PC2. You're going to square that one from 2 and 2. On the other hand, if you get your loadings, square that one, see, loading square, okay, that will equals to what? Eigenvalue. See, I'm talking about the loading. These are the loadings. This way we have the loading. See, if you square this loading plus this one and add together, you get the eigenvalues. This one plus this one, you get the eigenvalue in this direction. This direction you get the communalities. Community. This direction you get the eigenvalues. 1 over root 2, I go to my eigenvector or they are loading L1, sorry, not U1, loading. I'm going to square that one in this one, 1 over root 2, 1 over root 2. Then I get the eigenvalue 1. See? And the similar fashion, if I do the same thing for the second loading for PC2, I get the second. If you sum of these communities, on the other hand, sum of the communities for the variables x and y is equal to the sum of eigenvalues. On the other hand, same thing. Sum of the eigenvalues is same as the sum of the communities for the variables x and y. Same thing. If you go ahead and check your PC1, see, principal component analysis variance now. You go separately. Go and check the variance of the principal component. That's the variance of 1 over root 2x plus 1 over root 2y. This is the formula. You have a variance of ax plus by. Should be written a squared plus variance x plus b squared variance y plus covariance between 2 times ab covariance xy. I plug into that one everything that I have. See, covariance between x and y, you can remember it's -1 in the original. See, it's 1. Look at what is the variance of that principal component. That's nothing but the eigenvalue. See, so many things. Variance of principal component is same as the eigenvalue. See, that's the eigenvalue being. See, that's the eigenvalue. On the other hand, if you get the communalities, see, by squaring that in this one, this way, see, this way, how much being that explained by each variance of x being explained by PC and PC2, if you square that those two and sum them up, that will becomes the variance of x. And so does this. On the other hand, if you get the variance of PC1 is same as the eigenvalue, lambda 1. If you get the variance of this guy, it's lambda 2. That means that we have to decide that when you build up the principal component, these principal component, I have 2 of them. How many principal component to retain with us for our further that analysis? It's completely determined by, but there are several rules, criteria. Okay, but we can come to that one, but get a rough idea what's going over here. See, I built up this one. I did the same thing for the principal component, second one. using the same formula. See, and I came up with the same eigenvalue. See, eigenvalue, this one. Okay, don't worry about this one. See, 3. See? That means the variance of the principal components are same as the eigenvalues. Those variants are being distributed among these principal component in such a way that their commonalities, see, can be built up or constructed the way that we have over here. Okay. On the other hand, as I said earlier, that this is a physical interpretation behind this one. Okay, if we go further down to the physical interpretation or the graphical representation of this one, what I'm gonna do, look at this is the graphical representation of what we've been doing right now. You can remember, I have 3 points, 3 data points. One is 0, 1, the beginning. I'm talking about this one. See? I have this on x-axis, I have 1, 0, -1. On y-axis, I have -1, 1, 0. If you get those two, locate those on a xy plane, x and y plane, they will be located like this: 1, -1, 0, 1, -1 and 0. These are my, let's say that this is test 1 and test 2. This is x, this is y. So this is the code, this is the data vector. Can you remember data matrix? 1, -1, 0, 1, -1, 0. So they were located over here. See, their center is 0, 0. You saw that center. The mean value of this data would be here, just like a scatter plot in 2 dimensions. I'm trying to find a new variable in such a way that the projection from any point, I pick only one point at a time. Okay, 0, 1. Forget about the other 2 for time being. 0, 1, 2. I'm going to project that one to several lines in such a way that my distance from that point to that point of projection is minimized, while that the distance from origin to that point of projection is maximized in such a way that I pick any line that's going to go through this center. The distance from the origin to the projected point on the line. I'm going to focus on that one for time being, to physically. Rather than go minimize this distance, I'm going to try to maximize the distance from the origin to that projection, from that my point. I pick one point that will given that kind of a result. See, I say this is the line in which that I can get the maximum distance from origin to the point of projection. This has been maximized, this is being minimized, and through the Pythagoras theorem, you see, a squared equals b squared plus c squared, and I'm going to get this distance, this distance. I'm going to square that up. That's what we call the sum of square distance, which is called SSD. I'm looking for not only for this point, for all the points, 3 points. See? This C1 squared for this point, C2 squared for this point. I don't know the distance. Okay, I'm looking for a line that maximizes the SSD. That's what we call the principal component. That's a graphical representation. You saw that mathematically how we build that up. But graphically, that we are looking for a line that maximizes these distances. What distances? The distance from the origin to the projection from each and every data point to that particular line. So we are looking for such a line that maximizes the SSD. Those are I call the PCS. So on the other hand, sum of square distances for PC1 is nothing but the eigenvalue for PC1. That's lambda 1 again. See, lambda or that eigenvalue is again connected to this graphical representation. Sum of square distance for PC1. See, PC1, I think related to this one based on all the points, okay? All the original points. You say you decided I'm gonna get this line, okay? That line based on what? Based on the maximum value of this plus, this plus, this plus, which is called SSD, which maximizes the sum of square distances. That line has been picked as my PC1. If you need the PC2, you're going to draw another line perpendicular to that one. Look at it. If you take the eigenvalue for PC1, that's called the singular value. If I'm going to ask you to say, hey, can you give me the singular value for PC1? That's nothing but the eigenvalue, corresponding eigenvalue for that one, and its square root. See? So in a similar fashion, you can say SSD for PC2 is nothing but the eigenvalue for PC2, 3 is how they were being built up. See, PC1, you can remember PC1 is 1 over root 2 x plus 1 over root 2 y. And this angle, how do you get the angle? Angle, you can get this divided by this from the tangent. See, this angle, tan inverse, this divided by that will be that one. See, rise over run. Rise over run is same. 1 means 45 degrees. And your other one is perpendicular to that one. Is same as what? How do you get the angle? Angle is nothing but this divided by this, but negative. If you get the negative angle, this 45 here. See? Rise. This is rise over run. This on the vector. See? That's from the eigenvector. Eigenvector is nothing but the direction. Direction of PC1 is completely determined by whom? By the eigenvectors, the loadings. See, the loadings. In another way, loadings. See? Here the loading. That's how we got this. So you have a PC1, you have a PC2. See? How do you get the PC1? By maximizing the SSD. SSD is nothing but the lambda. How do you get the angle? You divide this by that. Your PC1 loading, this loading related to this one divided by that. How do you get this angle? And loading divided by this one. This negative, because of the negative, you have a negative angle. That means it with respect to the negative side of x 45. Look at the PC1, this is PC2. That's the graphical representation of that. Now, what are you going to do? That you're going to get rid of x and y and work with the PC1 and PC2. It's already been rotated. It's already been rotated. Do we really need the PC1 and PC2? No. If you really need another two variables to explain the third dependent variable, there's no point of doing this principal component analysis. We don't have to. We need how many of them will be discussed through a certain criteria. We have a criteria, okay? Before I come to that one, I'll show you, then I'm going to rotate this one here. I'm going to rotate back PC1 and PC2. See? PC1, let's say that anything more less than lambda, okay, more than lambda 1, more than 1, if lambda is more than 1, will be taken into account. That's one according to one of the Kaiser's criteria. According to Kaiser's criteria, there's one criteria. We're going to take anything, any lambda, any principal component whose lambda is more than 1. So I'm going to keep this one. Now I'm going to explain my response variable with the aid of this PC2 only. I don't need x and y any longer. X and y being already embedded within PC2. Why I pick PC2? Because based on one of the criteria say that, okay, you pick anything that more than lambda equal lambda, when the lambda is greater than 1, those are the ones that we're going to pick for our discussion. We keep those. So now I'm going to explain that my response variable, this one is called the principal component regression. Okay. That's the whole discussion over here, the rough idea. Okay. So in addition to that, if I add something back again, summarize what we did. Sum of the variance of x and y. Variances, x has a variance, y has a variance. Their sum is 4. The same as the covariance matrix trace. Okay. If you get the trace, it's the same as that one. It's the same as what? The sum of the communalities. If you get the communalities, 2 plus 2, that's again 4. It's same as what? The sum of the squared loading. If you get the loadings and square and then sum them up, that would be the total variance. It's nothing but the sum of the eigenvalues. See, in any way you can explain that the sum of variances. The variance being that split in such a way that at the end of the day, we're going to have a new variable called principal components. See? I'm not working with all the variables that been given to me. I had 2 variables. I say, no, I'm going to work with 1 variable. This is a new variable. It's very solid, concrete variable to explain the response. See? And then if you go to that, our example, how much proportion? See, so how much proportion being explained by each and everyone? See, look at proportion is 1/4 and 3/4 because the lambda. See, 1/4. Total variance is 4. How much being explained by the PC1? 1/4 of it. See, 3/4. If you go back to that, example that we were talking about in that example. See. Should go back to that one. See, this example. See, look at that for this cross state product data set. That if you run the principal component. See, now we have a 13. You know now how we got that these are the averages and standard deviation. This is the correlation matrix. Correlation of covariance matrix doesn't matter. See the eigenvalues. If you have a 13 variables, you have a 13 eigenvalues. There are differences between the 2 consecutive variables. See eigenvalues. Sorry, 2 consecutive eigenvalues are given here. See? And their proportion, how much being explained. See? The accumulation. How much to be, how many variables to be kept is that sometimes that you can guess by looking at. You say that I really need to keep that the total variance. These are variances. You can remember. See? Now, see, your principal component 1 is what? This time that, this time that. See? These are the loadings. You know loading means. We saw that in that example, how the loadings are created. See? They create 13 variables by default. If you want, you can suppress and say, I don't need the too many variables to be displayed. See, but anyhow, see, displaying all the principal 13 principal component will be generated with the aid of the older variables as a linear combination with their load weights. This time AG, this time mining, this time construction, this time manufacture, this time manufacture MD, see, the transport, communication, energy, trade, trader, see, services, government, see, recreational, right there. See, now we have a question, how many to be kept? See, you can, if you want, you can keep that principal components whose that eigenvalues are more than 1. See, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, using this scree plot. Scree plot is a graph between the eigenvalue versus the number of principal components. See? So this is one of the criteria. See, you can keep 1, 2, 3, 4, 5. See, 5 of them. See? Only these 5. Instead of working with 13 variables, now you can work with the 5 variables. See? 5 variables. That's the same thing that I'm trying to show over here. See that when you write, see, principal component 1 is nothing but 0.13 agriculture, but 0.43 mining plus blah blah blah, negative 0.38 services plus 0.29 government. That's the same thing that we see over here. See? I'm talking about here to here. This 0.13, I rounded that one to 2 decimal places. This to that time, this time this, and this time that, like that. See? It's a linear combination of the loading. These are loadings. On the other hand, this is nothing but the correlation coefficient between this guy and that guy, this guy and that guy. So in a similar fashion, I can keep going PC1, PC2, all the way up to PC4. See? I call them loading 1, 1, 1, 2 like that for my convenience. See? So that's a different one. Okay. That's a different example. Let's for the some other next example for that one. So keep going. You can write the whole thing like that, all the way up to PC5. Then, what are the criteria that we can utilize? Keep the number of principal components. This is the criteria for determining how many factors to remain using principal component extraction. Kaiser came up with that one. He said that eigenvalue greater than 1 rule. If your eigenvalues, Q stand for the index, how many variables, okay? Let's say that lambda 1, lambda 2, lambda 3. In our the SAS example, I have a lambda 1 through 13, 1 through 13, Q is 13, okay? And my in the book example, I have 1 and 2. Anyhow, if you stick to that example from using the SAS one, in the 13 one, see, any variable, any lambda greater than 1, you retain. Less than or equals to 1, do not retain, as I said. Okay, see, right there. The second one, see, Catters, the scree plot. In the scree plot, you're going to go to the eigenvalues are plotted against their ordinal numbers, just like that. The criteria say what? Criteria says see, magnitude of the successive eigenvalue drops off sharply, steep descent, and then tends to level off. Then you have how many lambdas to be kept, how many eigenvalues to how many principal components to be kept. Retain all the eigenvalues in the sharp descent before the first one on the line where they start to level off. Before they level off, all the eigenvalues will be kept. What's going to happen? They come and then at a certain point, it's going to be level off. But I don't see that one very clearly on this one. See, they are descending, only keep descending on this one. The scree plot, sometimes it's going to be very level off like this. If they are level off at that certain point, everything before that level off will be kept as our eigenvalues. Based on number of eigenvalues, we're going to keep the item principal component. That's another way to, but here in this example, I don't see that kind of a leveling off that much clearly. Here or even somewhere here, see, but it's not going to be consistent with what we did with the other criteria. The other criteria say anything greater than 1 will be kept. See, lambda is greater than 1, lambda greater than 1. See, here, 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 here. See, this is eigenvalue lambda. Those 5 can be kept, but it's not kind of like a not consistent with the second that scree plot method. But if you go to the textbook has some example in which that you can see all of a sudden it's going to be level off. Okay. And the third method is the parallel analysis. The parallel analysis we're going to do, we simulate the normal random sample that parallel the observed data in terms of the sample size and the number of variables. In our case, how many data we have. See, based on that data, let's say that if you go back to that particular example, let's go back to this example. See, observation 50 observations, variable 30. This is P. Number of variables P 13. The sample, how many people been involved with this one? How many states? 50 states. Sorry, here 50 states, 50. See, so your N is 50, P is 13. Okay. So what you're going to do in parallel analysis, it's another method that been put forward by their horns. Okay. You pretty much gonna see, simulate the normal random sample you generate. See, that Monte Carlo simulation procedure, you're gonna simulate. You don't have to worry about that one. That whole the code has been already given. Okay, the code has been given. See, sorry, see, it's the code. So see, factor analysis. So here parallel. See, from here to here, see, code has been given. Okay, in the even homework, you can see that one here. Parallel NS criteria, use the parallel NS program found here to identify the optimal number of factors. How many factors to be kept? See, either here or here. See, if you go straight, you can get that. Oh. Let's click this one. Yeah, see, you see, the whole code is over here. See, it's already provided. Okay, that Monte Carlo simulation procedure has been already provided. You don't have to worry about that one, and you have to change only the number of variables and number of. Sorry. Here, see, here, number of cases and number of variables only. See, how much percentage to be kept, why big the percentage, and how many number of data sets, see, number of variables, number of cases. You have to change that one only. But anyhow, what we're going to do in that one, that we're going to generate some simulate. We're going to simulate through the Monte Carlo simulation procedure. We're going to simulate the data with the same size and same number of variables from the normal distribution. See, then obtain the associated eigenvalues for each variable. You know how to get the eigenvalues for anything now. Okay, you know when you how do you get the eigenvalues? You go to the covariance matrix. How to build up the covariance matrix? You saw that earlier. You don't have to worry about that how they build up. But what I'm trying to say over here, even if somebody gonna ask you that how we built up the covariance matrix, you know how to do that. So once you have a data matrix, see this is the data matrix. How many data variables? P is how much? 2, X and Y. How many N? 1, 2, 3. See? So this one, and you're going to subtract what? For any data set, you know how to build up your covariance matrix. You can easily build up with if you extend the same idea for that 50 observation like this, 1, 2, 3, all the way up to 50. That means 50 rows. And how many columns? How many variables? 1, 2, 3, and 13 variables, 13 columns. Okay, so the same idea. And then later on, you're going to subtract their mean vector and then get the transpose between these difference, and then that will give you the covariance matrix one shot. It's already been done through the program, but I'm trying to say, even if somebody have any question on that one, you can even build up. And then from that one, you know how to get the eigenvalues. You know how to build up the characteristics curve even in 2 ways. One we did like this way, see, built up like this way. You don't have to go through this whole process. You can simply go over here and say lambda squared, trace of your covariance matrix, put over here minus that value, plus go to the determinant and plus here and solve that one. That will give you the eigenvalues. That program will take care of everything. And what we're going to do, I'm going to repeat this process again and again, k many times. I process that one and get the average of each and everybody. See, find the average of each associate eigenvalues average, because I have done this one k many times. See? K many times. Because of that, because this is like a simulated. I did the first time with the aid of the covariance. I just did that one. But if you go to the second round, second cycle, you're not going to have the same the normal random variates. Their values will be changed. That's why we have a different eigenvalue, different covariance. This different covariance will gonna produce you the different eigenvalues. Because of that, then you're going to average it. See, you average it. For given any I'm talking about you have a 13 variables for each and every one. It's been see each and every one. You can get the average. You can get the average for each and every one. See? You can mix everyone. See? Then find the distribution of eigenvalues for each variable. See, I'm just focusing on the qth one. Qth one means like it may be first one, second one, or third one, or the 13th one. I'm gonna rearrange them. See, from the first run, I got was this one, second run, the kth run. Then I'm gonna find. Okay, that's another way to do that. Either you're gonna go to the average one, or now you're gonna go to 95th percentile of this one. 95th percentile. See? 95th percentile. And you can do some kind of a little bit adjustment. With the adjustment, you can say, according to this one, see, subtracting mean, see, and this one, and you can adjust that one and come up with the, you're gonna subtract this much from what your lambda you had. Okay, that's called adjusted. Then, if it is greater than 1, you retain. If it's less than 1, less than or equals to 1, you do not retain. Or you can say with this one, you go with the average, or you go with the, see, there are 3 ways you can get this one. You can either with the aid of this one, you can retain, or with the aid of the average, you can retain, or with the aid of the 90th percentile, you can retain. In our homework, you can use any of these. I don't mind that in homework. If you want to discuss about through the parallel thing, they say parallel analysis criteria, use the identify the optimal number of factors. In that program, it's already that 0.95 has been given. Just stick to that one. See, stick to that one. That means that when let's say that principal component. I'm sorry. Yeah, here. Let's say with this one down. You see, percentile. From the percentile, you can figure out. See, this will produce with the aid of this one. See, percentile has been given. If you use the percentile, see, according to this one, if you go with the percentile, okay, the criteria says first, greater than percentile, you retain 0.95. It has been developed to go with this one, this criteria, not for this one or this one. Even under the parallel analysis criteria, there are 3 ways you can get this done, but with the aid of this adjusted one greater than 1, no, just regular lambda. See, your lambda greater than or this lambda. See, this is your lambda. See, this is your lambda. Okay, this is your lambda. Lambda coming from that the principal component analysis should be greater than the lambda coming from what? The parallel analysis. This is from PCA, this is from parallel. See, with the bar. But if you use from the principal, the parallel one, instead of going to the average, you can go to the 95th percentile and then compare contrast. Lambda Q stand for, okay, make sure that that's why I use that different notations. Okay, lambda Q is always for the original, see, original lambdas. Okay, original lambdas coming from your original data, lambda Q. Lambda Q R for your that if you do repeatedly in the for the parallel analysis, you use lambda Q R. For that one, those are the ones that we. So you, whatever the variable, let's say that you have a certain lambda like a 0.03, 0.03, compare and contrast and see whether this is going to be greater than 0.95. Okay, we can talk about that one tomorrow in detail. So these are coming from that Monte Carlo simulation percentiles. These are the percentiles. Percentiles already built up. So we can utilize this one and compare this one with the aid of, sorry, because it shows 8 because I didn't change that number of variables. Okay, if you go to the code, you can see clearly. Okay. Here it says 8, you have to change that one to 13. 13, and this should be see number of cases 50 like that. Let's run this one. Now we have 13 variables. Say, let's go to lambda 1. The principal component lambda, you know the principal component lambdas. Okay, let's go to the principal component lambda. I'm going to run that one for you. Oh, no, not for this one. I'm sorry that this one, I'm going to copy this one and paste over here under the PCA. Okay. 1 second. Related to this example, not the homework example.
Professor, just gentle reminder, it's 7:30.
Oh, okay. Thank you. Okay, okay. I'm gonna then thanks for reminding me. Okay, I'm gonna just show you something over here real quick, and we can just wind up and continue same discussion tomorrow. Okay, you know these ones, and related to this one, if you get the PCA, you go and see whether this value gonna be greater than the value coming from the first one. See, the 3 values. See, from when you run this one, you got the 13 of them percentiles, simulated lambdas, 13 of them. See, you compare with this guy. If it's greater than that, according to this criteria, we say our lambda, original lambda, should be greater than the 95th. See, according to this one, we return. If less, we do not return. Okay, so that's the kind of like a 3 criteria that the main 3 criteria is the criteria we I think those are the more than enough for us to that make sure that how many principal components to be retained at the end of the day. So that's a kind of like a rough idea, but we can, even when we go through the homework tomorrow and then even Thursday, we can discuss this in broadly because we have plenty of time now. Okay, but mainly that pretty much everything been covered, what I have to do, I have to put that more material on top of this one and then make solid discussion and then find that solution for this homework. Homework is not hard. Okay, you can see very easily. See, it's not hard. You can pick that any number of variables and then just find the univariate this one and then check that any issues you have with that one, missing data. If you have a missing data, how to remedy that one, you find that one, and those kind of and extreme outliers, how to detect the outliers, those kind of stuff. And later on, then you do the fact analysis too. Fact analysis, even that if you run this one, I what real quick run this one and show that. So related to this one, fact analysis is same as that I mentioned earlier. This one. Here, see. See, you get the factors this way. See, you don't write this way now. You write this way. You're gonna write the agriculture in terms of the factors. I don't go this way. I go this way. Agriculture being written with the aid of these loadings times the factor 1 plus this one times the factor 2 plus this one times factor 3 and this one times factor 4 like that. Those factors are unknown. These are late. We don't know which factors going to affect to that the agriculture that the gross state product. Don't know. See, we guess some, but if you're gonna go ahead and check with the what people have done earlier in the previous research, you can figure out what being what should be that for factor 1 through factor 5. How many factors to be kept, same kind of a criteria you can utilize, same criteria. How many factors to be utilized, because we're going to come up with the same thing, eigenvalue, same thing, same eigenvalue. But in a factor analysis, we're going to write AG in this way. The principal component, I'm going to write this way. Principal component will be written in terms of the given variables. And each original variable will be written with the aid of the unknown factors in factor analysis. Okay. We can, I think, build up this discussion broadly to further that tomorrow and the day after tomorrow. Okay. Do you guys have any questions before I'm gonna go ahead and then wind up over here, and then we can continue same discussion tomorrow and Thursday. Any question, anything?
Yes, Professor, I would like to watch the video tomorrow before class for the one for this class.
Mhm.
Do you think it'll be up?
Yeah, I can go ahead and then, because once we done that, I can go ahead and upload when its processing is done. I can upload like in 2 hours.
Awesome, thank you.
Huh? Is that okay?
Yeah, thank you.
Okay, thank you. Okay, then see you tomorrow. Have a good night. Just stay safe and be well. Okay, see you tomorrow. Take care. Take care. Bye bye. Okay, see you tomorrow. Hey, Raymond.